Okay, our next speaker today is Andrew Jenkins from AngloGold Ashanti. He'll be speaking on spectral geology, introduction and applications for exploration and mining. So Andrew, or AJ to those of us who know him, holds a BSc in Geology and began his career with Geoscience Australia and WMC. Since 2002, he's worked with AngloGold Ashanti and is part of the Australian exploration team. He's worked across 14 different countries for the company. He's been involved in early project generation activities globally and has contributed to a number of discoveries in Australia, in South America, in Colombia, and also in the USA. Andrew's passion is in connecting the information contained within spectral data with the unique objectives of a project, be that detecting alteration footprints from space with satellite system or vectoring it into high-grade mineralisation. He also enjoys integrating multidisciplinary data in software packages such as Leapfrog, MV, Iogas and ARC, and using machine learning to explore and discover new trends. Please welcome Andrew.
Thanks, Donna. Thanks, everyone, for joining us today. Yeah, look, today I just want to provide an introduction to spectral geology, provide some examples of how it can be used within the exploration environment and mining environments. So I'll cover some of the fundamentals on the technique, look at instrumentation, data, and then we'll move on to some real-life use case examples. So what is spectral geology? So sometimes I like to think of it like this, you know, like zapping stuff, making a mess, looking cool. But Geoscience Australia has a nice description on their website. Spectral geology is a measure and analysis of portions of the electromagnetic spectrum to identify spectrally distinct and physically significant features of different rock types and surface materials, their mineralogy and their alteration signatures. And that's actually a pretty good definition, which is why I put it up there. So maybe spectral geology is a bit more like this, like we're still zapping stuff, but maybe not so cool. Importantly though, you know, spectral geology delivers measures of mineralogy that are objective, repeatable, low cost, and non-destructive. And something just to keep in mind is that the mineralogy for each deposit is unique. You know, so the value is really about connecting the information in the data, in this case spectral data, but it goes for any type of data with the project's unique challenges and objectives. And I think that was mentioned a few times by previous speeches about, you know, horses for courses and that sort of thing. Okay, so in really simple terms, you know, the spectral sensors we use measures the reflectance of light in the infrared part of the electromagnetic spectrum. This spectral range has been the focus for geological applications because many minerals that we're interested in have distinctive and unique absorption features, which means they can be easily recognised. These features are caused by the bending and stretching of molecular bonds. So we're getting a view of the mineral's chemical and molecular structure with these data. Today, most handheld sensors cover the visible, near infrared and SWIR. We're starting to see the introduction of those that work in the mid and long range infrared. You can see on the right-hand side of the figure there, you know, such as Fourier transform infrared. So in contrast to our human eyes, you know, on the far left down there, we can just see within the visible part of the EM spectrum. So that's about 380 to 700 nanometers. And irrespective of whether we're using a spectral sensor on a satellite or one that we're holding in our hands, it works in the same principle illustrated here. You know, so we have a light source, that could be the sun, that could be a light bulb in an instrument. We illuminate the sample, it reflects, refracts, absorbs light, and we measure that with our sensor. And these are just a few examples of our sensors, our instruments that we collect the data with. They're highly varied, but they're all working on that same principle and all collecting the same type of data. You know, they range from the handheld instrument on the left there. This is the ASD TerraSpec. Some of you might have heard of this. There's also the ASD Halo, which is a slightly more portable version of the TerraSpec. We call all this point data, and so we hold the instrument or the probe to the sample. In this case, on the bottom left, we've got drill core, and we get one spectrum per point. So you can see just on that sample where the data has been collected. So most labs these days offer the service of collecting TerraSpec data, which is usually done on a composite sample after the drill core or rock chip has been crushed. Then we have, in the other examples, what we call image data. And for every one of these pixels in the image, it has its own spectrum. So analysing drill core, we have a pixel size of about 1 millimetre or 0.5 millimetre. We take the sensor further away, you know, we put it into a plane, and we start to have a pixel size of about 1 to 3 metres. We take that same type of sensor up into orbit. We've got a spaceborne sensor there. That's ASTA, and we've got a coarser resolution yet. So mineral spectra have characteristic wavelength positions, shapes, and multiplicity, and this results in diagnostic signatures that can be used to identify the minerals. And each one of the spectra on the left there relates to a pure mineral. So we can see each has multiple troughs or what we call features, so the various shapes, and we use those for our mineral interpretation. This is a nice table put together by Phil Harris. Summarises the response of our common minerals across the different infrared spectral ranges. You can see within the visible near infrared on the left, which is where our human eyes operate, most minerals lack diagnostic features, hence why colour is often considered an unreliable way to identify minerals. We've been mainly looking at and describing the shortwave infrared, which is where hydroxyl-bearing minerals, so minerals that have water within their structure, in particular hydrous minerals. So we've got phyllosilicates like the micas, chlorite, white mica, cerussite, amphiboles. They're very responsive, as well as clays, carbonates, and sulfates. The long-wave infrared, which is becoming more common in our geological sensors, enables us to see the tectosilicates. So that's the real advantage of the long wave. So that's things like feldspar and quartz, which do not have a good response in the SWIR. An important point down the bottom here, dancing away, is that all mineral classification techniques have limitations and inherent uncertainty. So whether it's infrared, XRD, the hand lens, classification using geochemical data, all these methods have their strengths and weaknesses. And as good geologists, it's important that we understand these weaknesses, understand the limitations, so that we can use the data correctly and wisely. Okay, from our squiggly lines, I'll just talk a little bit about the different data that's generated from the spectra. From our squiggly lines, often called curves in North America, there are a number of different data products we can produce. The simplest is a mineral classification, and in this case, this is a muscovite spectrum. So that's the interpretation we get there. Then there's what is known as spectral feature extractions, also called scalars, also called spectral parameters. All these terms are interchangeable. And these are measurements taken directly from the spectrum. So we can measure the depth of a feature. In this case, I think it's 0.28, I can't quite see there. we can measure the wavelength of the feature. So on this white mica spectrum, this main feature is called the aluminium hydroxyl feature, the ALOH feature. So we're looking at the wavelength of that. It relates to the chemical composition. We see cation exchange in a lot of minerals like white mica, chlorite, biotite, etc. We can measure the width of a feature. We can measure ratios to start getting indication of crystallinity of the minerals. And this produces numeric and categorical data that we can use in GIS and 3D. So from our data, we can measure the presence, absence of minerals, abundance. It's a semi-quantitative measure. We can measure the composition, where there's solid state solution in some of our minerals, crystallinity, ratios between mineral abundances, and mapping these changes is important because it maps out variability in a geological system. And that could be related to alteration zoning, which we can use for vectoring, could be related to fluid pathways, gives us information about weathering intensity, weathering depth, and mineralogy often has a very strong relationship with rock performance in the mining and processing environment. So mining could be slope stability, could be how the rock blasts. So making mineralogical models can help us map out some of these changes. All right, so now we're going to look at some real world examples. We'll start by looking at an example from a porphyry deposit. Most porphyry deposits have associated large-scale alteration footprints because they are fluid-rich mineral systems. So very hydrous magma, often enriched in metals such as copper, moly, and gold, is placed into the crust at a relatively shallow depth. As the magma begins to cool, a single-phase fluid splits in two. We see a vapor phase just marked by the blue arrows there, moving up and out to create what's called a lithocap, and a denser brine remains behind to crystallize and form our copper and gold-rich quartz veins within and proximal to the causative intrusion. As those fluids move through and interact with the country rock, they create hydrothermal alteration. At the deeper levels, the fluids follow a cooling path and maintain a relatively consistent pH. So you can see on this diagram on the bottom left, we can see the alteration mineralogy with that red arrow down at depth. It follows that cooling path, the pH remains consistent, and we go from minerals such as biotite, cave feldspar, and magnetite to the cooler minerals in the propylitic environment, such as chlorite, epidote, and calcite. In the lithocap environment, at the shallower levels, we see the fluids both cooling and becoming more acidic, particularly if interacting with meteoritic waters. So the alteration path will be across the diagram. So minerals stable under high temperature neutral conditions, like cerussite and chlorite in the base of the lithocap that you can see on the diagram on the right, that graduates through porphyroite, diaspore, and alunite as the conditions cool and become more acidic. Because of these significant gradients within a system, both in temperature and pH, we can see significant and measurable gradients in the mineralogy. This can be used to understand where we are at any point in the system. So if we have like a single outcrop or single drill hole, or if we've got multiple points, such as multiple drill holes, we can start to vector towards the more proximal part of the system. So this is data now from a porphyry deposit. So it's real data. The scale bar on the bottom right is 750 meters. It's approximately 80,000 meters of diamond drill core here. TerraSpec, Mag, SAS, SG, core photography, and multi-element geochem. So it was 4-acid ICP-MS, was done routinely on all drill samples. On the left is a downhole plot from a single drill hole with some of these data plotted. Gold and copper are well correlated, as you can see. They're anomalous from surface, but economic ore grades don't occur until about 400 meters downhole. So this deposit's actually what we call a blind deposit. So it doesn't have any anomalous copper or gold directly at surface, but there's lots of alteration. The objective data, such as the TerraSpec and the Geochem, were combined with the logging to build an alteration classification for each drill sample. The method that we used was to first establish what the alteration mineral assemblages were and their paragenesis, so that's their relative timing to one another. And then we selected parameters that best represented the presence absence of each one of those minerals. You know, for example, MagSus, not surprisingly, was the best measure of magnetite we had. TerraSpec was the best measure of cerussite, and the visual logging was the best measure of actinolite or epidote. All right. So on the right is the resultant alteration classification, the drill traces. Just moving forward, this is now simplified. This has been simplified to a scale that's more amenable to modelling, and that was relevant to the objective of this project. Further simplified again, where we took into account alteration paragenesis and a cross-section through the resultant model. And this type of model in an advanced project will form an input into mining, geomet, and our exploration models and planning. Now, if we stay at the same project and just turn back the clock a little to the very early stages, this is a project that AngloGold or a deposit that AngloGold discovered. In the early exploration stages, we were doing lots of work to try to understand the patterns evident in our exploration datasets. So we're looking at the geophysics, the geochem, TerraSpec, etc. A lot of holes we were drilling were intercepting anomalous copper and gold, but it was largely below ore grade. So we hadn't found the heart of the system. One of the datasets that we found useful was the downhole TerraSpec. And when we plotted the cerussite composition, so this is that measuring the wavelength of that aluminium hydroxyl feature that we looked at before. When we looked at that downhole, in this case, it's for a single drill hole, we saw a systematic variation through that phyllic zone, through the lithocap. We saw an increasing aluminium hydroxyl wavelength with depth. From our understanding of the processes that form the phyllic alteration, we interpreted that this systematic variation was related to changes in temperature and pH of the causative fluids. We also noticed that the rate of change or the slope of the gradient, so mapped with that red line there, varied between drill holes. Holes that tended to end in good mineralization had a slope like this one, like quite flat. Holes that ended in lower grade mineralization had a much steeper slope and even turned back towards the other direction. So in those early exploration days, we came up with this model. So I think we only had about 12 to 15 drill holes at this stage. Many of them were quite deep, so 2 kilometre deep holes. We predicted that the cerussite composition was mapping these gradients, the temperature and pH gradients. And most importantly, the rate of change could be used to estimate how directly a hole had been drilled towards a heat source, which was hopefully towards the hotter parts or the higher grade parts of the system. So you can see those 3 different illustrative examples there, with hole B drilled more directly to the porphyry, and you see the slope of that line, in contrast to, say, hole C, we are drilling sort of sub-parallel to the gradients, and so the change in the composition took on a different trend. And we did use this data in this way very successfully, and it is part of the discovery history at this porphyry deposit. And if we jump forward now to our 80,000 metres of drilling again, we can now build a 3D model of that exact same measure. We can build a 3D model of the cerussite composition. And that's what we have here, both in cross-section on the left and plan on the right. The blocks shown are only those with cerussite. So we've filtered those out that don't contain any white mica, and they're coloured by the cerussite composition. So warmer colours are the longer ALOH wavelength. So we can now compare our predicted model and the model that we used in those early exploration days with some real data. So I'm just going to use the next few slides to introduce the concepts of spatial and spectral resolution, which are terms often used when describing spectral data. Spatial resolution is the analysis window, such as with the Terraspec, you know, what we're actually seeing with that Terraspec probe. And with image data, it's the pixel size. Spectral resolution is a number of bands or band spacing that makes the spectrum. So more bands gives us more detail. We often hear about multispectral and hyperspectral data. Multi means some, hyper means lots, basically. These are two images over an exposed low sulfidation deposit. The aster on the left there is multispectral satellite imagery. It's got a pixel size of 30 meters. And the spect here is hyperspectral airborne imagery with a 2.5 meter pixel. You can easily visualize the difference in the spatial resolution of these two images, but we also need to consider the spectral resolution. Because across the SWIR, you can see in the table, Terraspec has 240 bands, Spectre has 122 bands, and Aster has just 6. So if we look at spectra from those three sensors, from this actual project, from the same location, you can see what they look like. So the spectral resolution of Terraspec and the Spectre is very similar, but both are far greater or far superior than the 6 bands of Aster. I remember when I came from a background interpreting terrestrial data, and when I was first shown Aster, I just had no idea what to do with it. I didn't think you'd get any information out of that very coarse data. The Spectre is a particularly powerful data set for mapping at this scale. When we consider that the spectral resolution is similar to Terraspec, and that this particular image is made up of 6 million pixels, it's like having 6 million evenly spaced Terraspec readings across the project. A bit more of a comparison between the multispectral Aster and the hyperspectral Spectre. These are mineral maps that I produced, another common product out of these remote sensing data sets. I'll zoom in, have a closer look. I think I've swapped sides there just to confuse you. So we've got the Aster on the right now. With the Aster, you know, the overall mineral zonation, and by the way, this is the original Aster data over this project. It hasn't been tweaked with ground control. This was the original data that was processed. And then the Spectre came along a lot later as that project advanced. So I think the Aster maps the overall mineral footprint quite well. It's captured but with the Spectre, it really takes things to the next level in terms of accuracy and resolution of those mineral assemblages. If you look at the legend down the bottom left, you know, with the Spectre, I was able to introduce a measure of intensity. So for example, I was being able to divide some of those alteration types, like the advanced agilic, up into a weak, moderate, and intense. And what really came out with those mineral maps was clear structural trends and clear structural controls, which is really important when you're targeting in an epithermal system. So was that 10 minutes? Yeah, it must be down to 8 now, I think. All right, so I'll try to move through this one quickly. It's just another example. We're still going to stick with image data. And we're going to zoom in at a much finer scale because this is now hyperspectral core image data. In each case, the pixel is 1 millimeter in size. So we've got about 30,000 spectra per meter of NQ core. It allows the spatial distribution of minerals to be mapped at that millimeter scale. It's a fantastic data set for understanding and characterizing alteration. Provides a very representative measure of the core's mineralogy, which is much better than, say, Terraspec point data. And it's useful for geomet modeling because it is much more representative. If you look at the diagram on the right, you know, we've got the carbonate veins colored in green there. You can go and click on any one of those spectra, one of those 1 millimeter size pixels, and each has its own spectrum. So this is a use case at an orogenic gold deposit. It started its life as open pit, as many do. It's since now full-time underground operation. Mapped on this diagram is drill holes coloured by gold. In the open pit, we had regularly spaced RC grade control drilling, and that meant that we could very accurately delineate the ore zones. In the underground, when we moved to that environment initially, it was very difficult to delineate that same mineralisation. We no longer had the RC, we were dealing with poorly spaced or irregularly spaced NQ-sized diamond, so our sample support was much less, and it became very difficult to delineate the mineralisation. Particularly the case because it's a very nuggety, high-grade or coarse-grained gold. The lodes pinch and swell in geometry over very small distances. The nuggety gold makes it difficult to estimate the drilling, and it's really important, a difficult concept, that just because the gold grade is low in the drilling doesn't always mean it's not ore, which is a little bit of a difficult thing to get your head around sometimes. But I've seen plenty of examples where a drill hole's going through what is predicted to be a mineralized structure, the grade's not there in the assays, you go and look at the core in the tray, and on the other side of the core, a piece of core that hasn't been sent to the lab, there's a big chunk of gold in there. So if that other piece was sent, it would probably run 500 grams per tonne. Instead, you're getting 0.5. So it's very difficult to differentiate between ore and a lot of anomalous smoke, we call smoke floating around, which are really small scale structures and cracks. And the advantage of using alteration in this case is that it's wider, so it provides a bigger target, and it's more consistent than the gold grade. So our mission for this particular project was, or we were asked to delineate the mineralized structures in the underground environment to the same level of detail to that achieved in the open pit. And it was really about trying to provide focus to underground RC grade control drilling. So that had been introduced. The drilling cost itself was low, but the development cost to put in that closely spaced drilling was very high. So we were trying to minimize the areas that were developed that were never going to deliver any ore. We scanned 100,000 meters of drill core across 2 campaigns. And then the real challenge became, how do we turn millions of spectra, or maybe even billions of spectra, into usable data? So we used our spectral feature extractions. We understood which minerals correlated with the mineralized structures, how consistent was the alteration. We targeted minerals like muscovite and iron carbonate, and we converted that image data into interval data. So because all the drill core was georeferenced, we could choose any interval we wanted. We chose 0.5 meters, and we looked at averages and pixel counts down there. So this is just the insight into a quick look at the data. On the left, we've got the RGB image, we've got cerussite composition, and then below that is the carbonate composition. With a TerraSpec, you'd never be able to go and pinpoint out all the carbonate because it just occurs as veins. But with this hyperspectral data, we could actually select out all the pure carbonate pixels and take direct measures off that. So that was a real big advantage of using this image data over conventional TerraSpec data. Really interesting was that the cerussite composition, which if we look at the columns in the middle there, is the middle column with the bright blue areas. All those pixels, a lot of those pixels have cerussite in them. So it wasn't about cerussite abundance. There's a lot of cerussite. There's a lot of different stages of cerussite, but it was a very particular composition or phase of cerussite that had a very consistent correlation with the mineralization. And each one of those blue intervals is marking out a fluid pathway that's related to our orogenic gold. So we combined all our individual measures into an alteration index, gave us a score of 0 to 12. I think this sort of touched on, I think Carl mentioned about having indexes with multiple parameters combined. 0 was unaltered or 12 was strongly altered. We can almost think of this index as a likelihood of a piece of rock to be mineralized. We built 3D models of that, wireframes, block models. If we take a cross section and look through that, we'll just look at maybe the top left image. This is a slice through that wireframe. That's all the drilling that was available with gold assays. To the right of that is all the drilling we analysed with the hyperspectral. It was about 20% of the drilling that we analysed. And the very bottom right, they just started to do grade control drilling in this area. And this was the grade control model, or the block model that they built for gold compared to our alteration wireframe. And you can see it, the alteration wireframe pulled out quite nicely one of the best and well mineralised structures. So I'll skip through this example because of time and just wrap up with a summary. Spectral geology provides objective and measures of mineralogy. So we have different sensors with different spatial and spectral resolutions. All mineral classification methods have inherent uncertainty. So they all have their strengths and weaknesses. So really key point there is to know your data so you can use it in the correct way. There's applications that scales from the millimetre right through to the kilometre. You know, if we're mapping mineral systems with Astra and trying to identify in our early target generation stage, and equally applicable through to exploration and mining settings. In mining, the mineralogy improves ore body knowledge and provides and assists tactical and strategic planning. Sometimes just having that data available in the mining environment will encounter a problem. It could be a deleterious mineral. It could be talc. It could be swelling clays. And if we have data that can map that out, we can very easily turn to that and look at our models and help us manage that problem. With exploration, it assists in understanding the mineral systems to aid targeting and assessment of a project's potential, particularly in the early stages. And the mineralogy of each deposit is unique, as I mentioned before. Thank you.